Kirchhoff's laws. In that, KVL, Kirchhoff's voltage law and Kirchhoff's current law that we discussed. Yes. So today we are taking the next part of that is the Wheaton's bridge. Yes. So what it is then? See, Kirchhoff is a scientist. With his name they given the law. Correct? Here also similarly Wheaton's network is nothing but the Wheaton is also a one scientist. With his name they given the network name. Yes, that's why we call it as what? Wheaton's bridge or else the network. Yes, so here also we are considering the more than one resistors. Here we are mainly considering the 4 resistors. Yes, then why we use the Wheaton's network here? See, in order to compare the resistance values in the network, we are using the Wheaton's bridge. Yes, what I told you, in order to compare the resistance values in the network, we are using the Wheaton's bridge. Yes, see, by using the formula of this Wheaton's bridge, we can easily calculate the resistance values. Like if you know the 2 resistor value, then you can easily calculate the other 2 resistors. Or else if you know the 3 resistors value, then you can easily calculate the 4th one. Understood? Like this, it is very helpful to us to calculate the resistance values. So here you have to remember the formula, and it is also very important for your exam purpose. Take it as important, because they may be asked you for the 5 marks. Yes, this derivation is very important for you. Okay, then see, just remember this formula. In the CETs and the JEEs, they will ask directly the question on this. So if you know the formula, then definitely you can solve. Okay, so let us start with the explanation part. Then it is a mathematical form designed by the Wheaton for the comparison of the resistance. See what it is? It is a mathematical form that will be designed by the Wheaton. What is his name? Wheaton, in order to compare the resistance values. Yes. So basically consisting of the 4 resistances, that is R1, R2, R3 and R4, connected in a form of quadrilateral. What they said? They are connected in the form quadrilateral. That means how? Here. See here, just you consider this as a resistance 1, resistance 2, resistance 3 and resistance 4. They are connected in the form of quadrilateral like this. Yes. So after that, a galvanometer connected across the BD for the measurement of current. So here we are considering the galvanometer. Yes, that is connected in between the BD. See, take it as point A and it is point B, it is point C and it is point D. So in between the BD we are connecting the galvanometer. Just tell me students, why we consider the galvanometer in the networks? Yes, in order to measure the current. Yes, with the help of the galvanometer we are measuring the current. That's why we can easily measure that current that is present in the network. Now you are having the 4 resistors R1, R2, R3 and R4. They are connected in the quadrilateral form. Clear? Later we are connecting the galvanometer in between the B and D point. Understood? After this, the EMF or else the cell is connected in between the point A and C. Yes, in between A and C, one cell is connected which is having the EMF E. Yes, so now through this network the current will flow, because here the cell is present means of course the current will flow. Yes, the actually total current will be I. Yes, but when the current enters resistance. So we can call it as I1. So here it is I1 and here it is coming and it is become I2. Next, and a point will come here and later it starts to move down. So it will take it as I3 and here it is coming down and it will go like this. So it is current I4. So the total current will be splits into the different branch of the current. Yes, that is I1, I2, I3 and I4 are the different branch of the current. And here one more branch will passes through the galvanometer. What is that? Here, see, from the B to D, the current will passes because the network is present. Yes, and that is passing through the galvanometer. That's why I named it as IG. What is that? IG. Current through the galvanometer. G is nothing but galvanometer. Understood? So later, when the current I enters the network, it splits into the various branches as shown in the figure that I already explained you. Then by adjusting the resistance, we can make the IG is equal to 0, which is known as the balanced condition. See, it is very important for you. What we will do here? By adjusting the resistors. So here in this network, we are adjusting the resistors. And after that, what we will make? IG equal to 0. What is that? IG is equal to 0. That means the current through the galvanometer must be 0. That is the balanced condition for the resistance bridge. Understood? This is important for you. Yes? What is the balanced condition? Making the resistors adjust and IG will become 0. That is the balanced condition for the this network. Understood? So here by adjusting the resistance, we can make the IG is equal to 0, which is known as a balanced condition. Yes, they may be asked you for the 1 marks. What is balanced condition? Yes, by adjusting the resistors in the network, we make IG is equal to 0. This condition is important now. IG is equal to 0 and we can call it as balanced condition. Yes, so this is all about the just theory part. Now we will start the derivation for that. Okay, so then the expression for balanced condition for the resistance network. The expression for balanced condition for the resistance network. So for the balanced bridge, we have the condition. What is that? First you have to write this one. In order to determine the expression or else the mathematical equation, you have to start with the balanced condition. What is that? IG is equal to 0. Yes. So now such that there is no current through the galvanometer. See, here IG is equal to 0 is nothing but the current through the galvanometer must be 0. So the current passing through this galvanometer must be 0 because balanced condition. Yes, that we adjusted. We adjusted the resistors, so it became 0. Understood? So after this, just remember now I1, I2, I3, I4 and the IG currents. These are the different branch of the currents that passes through the resistors R1, R2, R3 and R4 and one more will be the through the galvanometer. Correct? So now in resistance KCL at the node B. See, now we are going to apply the KCL law. KCL means Kirchhoff's current law. Yes, Kirchhoff's current law. What it says? Incoming currents equal to the outgoing currents. Understood? So now apply. Here at the node B. Here we are applying now KCL law at this point. So how many currents are present here? One is current I1, one is current I3 and one more current will be the IG. See, these three currents will meet at studied that if the current is coming positive, if the current is going, then it will become negative. Yes. So the current is I1 coming towards the B, so positive, and I3 moving away, so take it as negative. Then of course the current Ig is also moving away from the point B, so take it as negative. See, already you know that Ig is equal to 0 from this, correct? So put it as 0. So what remains? Only I1 minus I3 is equal to 0 remains. So take this at that side. So I1 is equal to I3. Correct? So that only I written there. This one. Now similarly for the node D here at this point. Now here also the three currents. One is Ig and one is I4 and one is I2. Correct? So now see, I2 is coming towards the D, so take it as positive. Then I4 is moving away from the D, so take it as a negative. I2 minus I4 and again the minus Ig. It is also, take it as plus Ig because it is coming towards the D, no? So plus Ig. Yes. So now what will happen? Again Ig will be 0. So now we are getting that I2 is equal to I4. Correct? So by doing this we come to know that the current I1 is equal to current I3 and current I2 is equal to current I4. Yes? So after this we are going to apply the Kirchhoff's voltage law. Yes? See, first we apply the Kirchhoff's current law. Now we are applying the Kirchhoff's voltage law. Yes? So apply to the mesh ABDA. See, for the loop or else the mesh we are applying the voltage law. Yes? First one is the ABDA. Correct? So like this you apply in the clockwise. Yes? In the previous case I told you. See, while explaining the Kirchhoff's voltage law, clockwise direction we will consider. Yes? So now first one, applying KVL to the mesh ABDA. ABDA. Yes? So first one, see, it will comes like this. Yes? So now I1 and R1, this is in the direction towards this clockwise. Yes? So take it as I1 R1 as a positive, and then see Ig into G, it is also in the direction. Correct? So plus Ig into G, but I2 is moving away. See, this direction is upwards, current is downwards. So of course opposite to each other, right? Current is coming downwards, but we are applying the clockwise direction. It is showing upwards, right? So I2 minus I2 into R3. Yes? What I wrote? Minus I2 into R3 is equal to 0. But we know that Ig will be 0. 0 into capital G, nothing but of course 0. It will become 0. Yes? So put I1 R1 is equal to I2 R3. Because if this negative sign goes that side, it will become positive. I2 into R3. Take it as an equation number 1. Yes. Then similarly you apply the Kirchhoff's voltage law to the mesh BCDB. Yes. Now for this BCDB, here also same clockwise direction. Yes. First we applied for this for that ABDA. Now we are applying BCDB. First one for this half and now for this half we are applying. Correct? So now also we are applying clockwise. Correct? So what we are getting now? I3 into R2. Positive. See, it is also moving like this. Yes? So I3 into R2. Take it as positive. Minus I4 into R4. See, but current is moving that side. Yes? This is upwards, but the current is now downwards. So opposite, of course, you have to take the negative sign here for the I4. minus I4 into R4 and minus IG into G. See, this is also coming downwards, but this is upwards. Of course, here also it will become minus Ig into G. So, you already know that balanced condition Ig will be 0. So, put it as 0 and what remains? Only I3 into R2 is equal to I4 into R4. Because if the negative sign in this side, it will go to that side, it will become the positive. Understood? So, just what you do here in this equation, you put I1 is equal to I3 and I2 is equal to I4. Just we are changing the currents. From this, I1 is equal to I3 and I2 is equal to I4, no? Here, put I3 is equal to I1 and I4 is equal to I2 in order to balance. Then, what you will get? See, I3, here I wrote I1, same R2 is equal to, instead of I4, I am writing now I2. Then R4 in same, here also same. So take it as a equation number 2. Now 1 divided by 2. So equation 1 will be divided by equation 2. Yes. So equation 1 where it is here. I1 R1 divided by I1 into R2. I1 R1 divided by I1 into R2 is equal to I2 into R3, I2 into R3 divided by I2 into R4. Yes. So what you will get? I1 get cancelled, I2 get cancelled. Yes. So what remains at final? Only R1 divided by R2 is equal to R3 divided by R4. This is the mathematical expression for the Wheatstone's bridge. Understood? It is very important. See, if I know R1, R2, then I can easily calculate R3, R4. Yes. See, if I know R1, R2, R3, if I know 3, then definitely I can easily calculate the fourth resistor value. Correct? So, by using this mathematical expression, I can calculate the value of the resistors. Yes? So, this is about the Wheatstone's bridge. Understood? See, here we are using the EMF E. If I placed whether it is a high voltage cell or else a low voltage cell, whether there is a problem it will make to this network. What actually I said you? See, already we are placing the, just consider here the 5 volt cell I placed here first. But if I place it now 10 volt, so voltage will becomes high. Whether it affects to this bridge? No, it will not affect. Understood? And the current also. See, first I am supplying the less amount of the current, but later I supply the more amount of the current. Whether it will changes to anything to this network? No, it will not affect. Yes, but if this R1, R2, R3 and R4, what I told you, if R1 is equal to, R2 is equal to, R3 is equal to R4, if this condition is there, then there may be some variation will occur in this network. Understood? So these are some points I want to discuss with you today. Okay? So today we discussed about the Wheatstone's bridge or else the network. See, the derivation is very important for your exam purpose also and for the practical purpose. Okay? So just practice it, and in the next class we will take the next part. Thank you everyone.